Hello. I'm Navon, and I'm going to speak about cube versus cube low degree test. This is a joint work with Amey Ben-Gale from Rutgers University and Iridinor from Weizmann. So in general, in this work, we're looking for a low degree test in the low soundness regime. And this means that we're looking for some kind of a structure of a property in an object that has barely any kind of local consistency, that almost always, when we try to query it, we fail. But still, we succeed to find some kind of a global property. And the global property that we're looking for is this object being a low-degree polynomial. So I'm going to start by explaining what is a low-degree test. Low-degree tests are one of the first properties that were studied in property testing. They were studied since the 90s, and they're important in constructing PCPs. But what is the test? So we have some function f from a finite field to the end to this finite field. And what we want to know is this function f a degree d polynomial? Now, we're not getting the function f as coefficients of a polynomial, but there is some large table where for each x, we can query f of x. And of course, we could query this entire table and then use extrapolation and find out. But this is going to take really a lot of time and really a lot of queries. So instead, what we want to do is property testing. We want to query this function f on a few random points and then decide only by the points that we've read. As people said already before, in property testing, we can't distinguish between really close functions because we're just not going to read this difference. So instead, we want to distinguish between a function that is a degree d polynomial and a function that is far from a degree d polynomial. So this is what we want to do. Now, how many queries do we have to do that? We have to do at least d queries to query f on at least d points if we want to remain, because even if we restrict f to a line, we still have d plus 1 coefficients. And if we read it on d points, we can't reject anything because there is some low-degree polynomial that fits what we've read. So we have to know f on at least d points to be able to know that. But then, suppose we don't want to query it on d points. We want a constant number of queries. And preferably, we want it to be as low as possible, which is 2. So what can we do? So an idea that came from PCP, Alon et al. In the PCP theorem, was to ask for a proof that this function f is a low degree. And their proof considered of f restricted to a line for every line in Fm. This way, on a single query, we get f on an entire line, and we can check it. But this way, we also have to verify that this proof has the correct structure, because maybe someone cheated. And this proof for L, it contains f of L, but from a different line, L2, it just contains some different value, which is not the same function f. So a way to test it is to look on two lines that intersect on a point and see if they agree on this point. So this is the general agreement test. And so now we forget about our original function f, and we in fact only care about this proof. So we're not going to call it a proof anymore. We just suppose that you have some table that for every line, it considers some function restricted to a line, meaning it gives a value for every point on this line. And what we want to know is this line corresponds to a degree d polynomial, meaning either some degree d polynomial g, that for every line, it's restricted, t of L equals the restricted of g to L. So this is now the new question we have. And as I said before, if this t actually is a degree d polynomial, then every two intersecting lines, L1 and L2, t of L1 and t of L2 are both degree d polynomial, and they agree on the intersection. Now, the converse also holds. If you have a table that has perfect agreement and is always a degree d polynomial, then in fact it corresponds to some degree d polynomial g. But what low-degree theorems are about is what happens if this table doesn't have this perfect agreement. But on most cases, it agrees. For example, if it almost always agrees, if almost all two interacting lines agree, do we still have a single degree D polynomial? So the answer for that is yes. So more formally, if we have a test that chooses a random point and then two intersecting lines on this point, and accept if the entries that he reads are degree D polynomial and they agree on the intersection, so suppose we denote by alpha the probability of this test to pass, then Alon et al. They proved that if this alpha is 1 minus delta, then there exists some degree D polynomial that agrees with what we might expect, which is almost 1 minus delta of this table. So there is some kind of a noise. Some entries are bad. But generally, this table corresponds to a degree D polynomial. In many cases, if we want to have low soundness PCP, what we want is a low degree test that does not succeed with probability 1 minus delta, but actually we want a test that also succeeds when this alpha is almost 0. So in this case, we can't expect to have a single polynomial that is close to all the tables. The best we can hope for is that if alpha is larger than some threshold, tau, then there exists a degree D polynomial G that equals the table on omega alpha fraction of the table. Because we only have alpha agreement, we can't expect more than alpha of degree D polynomial, because the rest of the table can be complete junk, and it's just going to fail every time we read it. So when we started to look on this problem, what we wanted to do is to get a low degree theorem for the lowest agreement possible, which means that it is the lower threshold tau. And you might ask, why do we even need a threshold? Why can't this theorem work unconditionally? So if we look on a completely random table, for every line, we just choose a random degree D polynomial, and we fill it. So this table is still going to pass with probability 1 over the field size, because two random values in the field will be equal with this probability. But this table has no structure. It is not close to anything. It is just a random table. So the tau, the threshold, has to be at least 1 over the field size. And what is interesting is what happens if it's slightly more. What it is if it is like a constant 100 over the field size or more. So can we have a structure in the case where it is just slightly above what a completely random table would give? So this was the main open question we wanted to solve when we started to look on this problem. And I can give a spoiler, we didn't get that far. But we did get a lower threshold than was previously known. So I'm going to start with saying what was previously known, and then present our own theorem. So this is the general structure, as I said, of low degree theorems in the low soundness. And what we care about is the dependency on the field size. So we assume that the field size is much larger than the other parameters in the question, which are m, the dimension, and d, the degree. So on 97, Raz and Safra analyzed plane versus plane test. This means that instead of having a table of lines, they had a table of planes, and they chose two intersecting planes. And their threshold was 1 over the field size in some power c, which is smaller than 1, that they did not calculate. In the same year, Aurora and Sudan had a low degree test. They analyzed line table. And they also had an unspecified polynomial in 1 over the field size. On 2008, Moscovich and Haas has a different object of their paper, but they also had the first explicit power of the field size, which was 1 over 8. In our work, we analyzed cube versus cube test. So our table has to be now a table of cubes, which are dimension 3 affine subspaces. And the threshold we got was 1 over the square root of the field size, which is much lower than was previously known, but still it is not 1 over the field size. So we have this factor of square root that we can't get rid of.
Do you think one can get rid of, or do you think there might be more non-trivial reasons for why?
I think you can go lower than 1 over square root. I'm not sure you can go as low as like 100 over the field size, but In our technique, it's completely impossible. Like, we got stuck in more than 1 point on this.
The C in the first two results, that's like C that's less than 1, but it's close to 0, right?
It is less than 1. They did not calculate it at all. So we just know that it's some constant.
Okay, but it's probably close to 0, that's what you're implying.
Well, yeah.
Like it's a bad C.
If it was a good, usually if you can get good C, you figure out what it is. But sometimes it's just too complicated. Like the analysis, as Sandra said before, the analysis of this is much more complicated. So it's also much harder to know what C you're actually getting. I think the main idea of Moscovich and Raz is similar to Raz and Safra, but they managed to do the analysis. So our analysis is much simpler, which I think is why we know that this is definitely we know that this is the best we can get.
But for example, you think that the analysis of Moscovich and Raz can be extended to plane versus plane to show like some explicit C for plane versus plane?
Moscovich and Raz had an explicit C.
Yeah, no, but it's plane versus point, and it's not a big deal like to move
I
it.
think it doesn't matter because
They're
if
like
you
close
have
to
a
each other.
point table, you can always fill it with the most common value, and then there is like the success probability of plane versus plane and plane versus point is not much different. Okay, so I'm going to now formally state the test and then our result, and then I'll give a little bit about intuition about how we did a proof. So the test is cube versus cube test. So we choose a point in Fm, and then two random cubes, which are dimension 3 Fn subspaces, that intersect on this point. And we accept if we read entries that are degree D polynomials and consistent. So again, we denote by alpha the success probability. And our main theorem is that if alpha is larger than 1 over square root of the field size, I mean some polynomial in D, then there exists a degree D polynomial G such that T of C equals the restriction of D to C for omega alpha fraction of the table. So this is the main result. And now I'm going to give like some idea about how we wanted to do it. So in general, what we're looking for is some function that is close to many of the table entries. So a very natural thing to do would be to take the most frequent value. That is, we have some, for every x, we can look on all the cubes containing x. Each cubes give us some value for x, and we can just take the one that appears the most frequently. So, will this work? This doesn't work here. This kind of method only works when alpha is close to 1. So why doesn't it work? We can look at the following example. We have 3 different degree D polynomials, P1, P2, and P3. And each cube has a restriction of one of these polynomials at random. So this table, if you look on the test, will pass the test with probability about 1/3. Because if we hit the same polynomial, we will pass. If we don't hit the same polynomial, we almost always fail. So definitely this theorem holds for that. But if we take the most frequent value, it might be that for x it's going to be P1 of x, but for y it's going to be P2 of y. And in general, what we get is the function that equals P1 in about 1/3 of the table, P2 in 1/3, and P3 on 1/3. And this is not close to a degree D polynomial. It is also not close to any of the table entries, because this entry, for example, is P2 on the entire cube, not on 1/3 of it. So what we would want to get is somehow a way to extract one of these polynomials from the table. For example, P1. If we had like, I don't know, someone would tell us, look, if you look only on these blue entries, and you take the most frequent value on these, then you would be good. You would get a degree D polynomial. So how would we know which entries should we look at? So what we do is, we use an idea that happened in direct product testing in Palazzo Cabanets and Wigderson in 2012. And the idea was to look only on a single x, and only on cubes that contains x, but also that if x some specific value. For example, in this case, we take P1 of x. These are going to be these two cubes. Now, if we would only ask these cubes, then we would be good, because all these cubes give the value P1. Since 2-degree D polynomials differ almost always, it is very unlikely that we get here anything except P1. So what does it mean we ask these cubes? For every y, we look on cubes that contains both x and y, and they give x the value P1 of x. So these cubes obviously gets P1, and we'd be happy. But what we need to show is that there is always such cube. Maybe if we have these two conditions, then we have an empty set. There is no cube that satisfies these two conditions. So this is, in fact, one of the reasons we had to go to cubes, which are dimension 3 affine subspaces. Because we wanted that even a small fraction of all the cubes containing x would also contain y for every y in Fm. So if we would take lines, a small fraction of the line containing x does not cover enough of our points. So here we had cubes, which is enough to define a function that is good. Now, in this case, this actually finishes the proof. We got P1, we are happy. But in general, we don't know that this is the case. So what we need to show is that the function that we've defined this way are actually good. And this is what we do in the global structure. So what we got previously are many functions f of x, and each of them is defined by the most frequent value on some subset of the cubes containing x. And in the global structure, what we actually do is that we find one of these x's that is globally good, that its function f equals the table on about an alpha fraction of the table. And the way we do it, we use some spectral properties that I don't have time to speak. So also, if you are interested, you can ask me in the poster session. So we use spectral properties, and this is in fact one of the places that we get stuck on square root of the field size, because we use spectral properties of graphs, and the graph eigenvalue is 1 over the field size, so we can't prove anything lower. So so we find some function f that is globally good, meaning it is close to the table entries for many cubes. And then we show that this f is actually close to a degree D polynomial. In the example, we got P1, which is a degree D polynomial, but in general case, this may not be. So then we show that. And this is the general outline of the proof. So I'm going to finish by speaking about open questions. So the main thing that remains open is, can we go from 1 over square root of f to some constant over the field size? And we can think that maybe we can relax our conditions a bit more. For example, we can use even higher affine subspace than cube. Obviously, if we get to m, that's not helpful. But if we can get to any constant, like 4 or 5, this will also be interesting. And another way we can relax it is we limit a degree. So this work was for any constant degree d. And you can think about maybe even d equals 1. Does it help us? And another thing that is open is to figure out, is the cube was necessary? Because in our analysis, we had to go to cubes. But generally, this might not be the case. So, thank you.
In your table of results, one of them had dependence on M and D, the other
Yes.
only on M, the other only on D.
Yes.
Is it clear that any dependence on either of the two is needed at all?
So we didn't have a dependency on M. So obviously, this is not needed. And the reason is the way they did the proof. The dependency on M happened because the proof was in induction over the field size. So then you get accumulated error with the field. And we didn't have induction. We were doing it straight, so we didn't have dependency on M. I'm quite sure that the dependency on D, some dependency on D, is necessary. D over 4 is definitely not best. We, in our analysis, can reduce it to D to the power of 3. But I'm quite sure that some dependency is important.
You're saying that the optimal bound is closer to CD over F, or?
So I think if it's even like d over f or something, this is by intuition. I don't have a counter example, but I'm guessing that there should be some factor.
Between plane versus plane and line versus line, which one would you attack first? Or
Well, definitely planes is easier, as long as each time you read the larger chunk, it's easier to analyze. But this would require a completely different technique, because the way we did it, we had to use cubes. So it's not like I have some idea about how to do it.
okay, let's thank you, again.